How we doing? Good. So get test backs. Some were good. Some may not be where you wanted them. I would encourage you to reach out for help because, again, like I mentioned several times, factoring is not going to go away. You know, that was the bulk of the exam, right? Being able to factor. As a matter of fact, we're going to be doing some more factoring today to be able to do the types of problems we're going to talk about. So come see me, head to the Math Center, go to there's a supplemental instructor for the course as well. Got lots of resources. I'm happy to go over anything that you missed. Get the the exam key posted on Moodle as well if you want to go through that and see what you missed on there. All of those good things. So, like I said, just reach out when you got questions. I'm happy to go over things, always. All right. Well, let's talk about new stuff. So, we've talked about what a polynomial is, and we've talked about factoring. So, we're going to combine those two ideas together here when we start talking about rational expressions. So, notice in the notes here, it tells you that a rational expression is a fraction. Notice that the root word of rational there is ratio. All right, so we're talking about a ratio of something. You've dealt with rational numbers before. Those are the fractions. Okay? Fractions are written as one whole number over another whole number. Okay? So this is kind of an extension of that. If you think of your polynomials as kind of the whole number piece, then a rational expression is one polynomial divided by another polynomial. Okay? So that's all it means, is that we've got polynomial on top, polynomial on the bottom. Right? So again, remember with your polynomials, your x's, when you see an x, the exponent has to be a positive integer, meaning we don't have any negative numbers up in our exponents. We don't have any fractions up in our exponents. Okay? So in our polynomials, when we see an x, that power has to be a positive whole number power. Okay? So notice in these expressions that are listed in here, all of these are one polynomial divided by another. Some of them are a little bit simpler polynomials than others. Remember that when we have just a simple number, like a constant here, a 7 or a 4 or anything like that, that's still a polynomial. It just doesn't have any x's in it. That's okay. We can think of that as an x to a power, which we'll talk about later. But anyway, all of these are rational expressions because you've got one polynomial divided by another. What this rational expression stuff allows you to do is something that we did not see with polynomials, and this is allowing x's to be in the denominator. Okay? Notice when you have a polynomial, there aren't any x's in the denominator. Rational expressions is the first time we're allowed to have x's in the denominator, but we have to be careful when we have that. Okay? So this last part here, notice that we've got something like 4 over x minus 3. If we try to plug in a number for x, I have to be careful when I start introducing denominators. What number can you not divide by? 0, right? So I have to make sure that whatever I plug in for my x doesn't make the denominator equal to 0. Okay? We refer to those as restrictions. Okay? So in this case, when we have this 4 over x minus 3 piece, we say that the restriction is for all x not equal to 3, because again, we cannot plug 3 in for x, because that would make a 0 in our denominator. So a lot of times when you're looking for restrictions, you're going to be setting the denominator equal to 0. Well, the denominator is a polynomial. We just solved polynomial equations for this last test, right? So you can see where that concept is going to pop up as well. So we'll see examples of these. Let's do this first one here. We've got x squared plus 3x minus 10 over x squared plus x minus 6. So on a lot of these problems, you'll be asked one of two things. I'm going to ask both of them when we do this example. The first thing I'm going to ask is, what are the restrictions? Okay? Or the restriction, I guess I should say. So again, the restriction comes about by looking where the denominator is equal to 0. The bottom is equal to 0. Because again, what can't we divide by? 0, right? So anytime, all the restriction is asking you to do is take the bottom, set it equal to 0, solve, and that's what x can't be. Okay? That's what it means by the restriction. Okay? All right, so the bottom here is x squared plus x minus 6 equals 0. And we're going to solve this just like we did in the previous sections. We're going to factor that left-hand side of the equation. And we'll set each factor equal to 0, just like what we did for the exam, right? How does that factor? Good. If you need to use the AC method, that's perfectly fine. But remember, when we have those polynomials that have a leading, the quadratics that have a leading coefficient of 1, we know we have to use x and x for the first terms. I need things that multiply to -6 and add to +1. So we use +3 and -2 for those. Okay. So now set each piece equal to 0. So we have x plus 3 equals 0 or x minus 2 equals 0. So the first one gives you x equals 3 or x equals 2 in the second one. Now again, these are the numbers that make the denominator 0. Those are the bad ones, right? So we want to throw those out. So your restriction then will be x is not equal to -3 or 2 would be your final answer here for restrictions. So by setting the denominator equal to 0, we're finding the bad places, right? We're finding the bad numbers to plug in for x. That causes issues. Does that make sense? Okay. So that's one thing that you might be asked to do. Notice, though, you may have already noticed that there's a different set of directions here. For the examples that we have down here, it says reduce the lowest terms. Basically, you've done lowest terms when you've done fractions before with numbers, right? You're trying to cancel out common factors. For example, if you had something like 12 over 18 and you were asked to convert that to lowest terms, what number goes into both the top and the bottom? 6 does, right? 6 works. So this is the same thing as 2 over 3 because you can cancel a 6 on top and bottom, right? If I wrote that out longhand, the top is 2 times 6, the bottom is 3 times 6, and then you cancel, right? Or divide out. Yeah. We're going to do the exact same thing, except that it has letters in it instead of numbers. Literally the same exact thing. We're going to factor like I did here, right? I wrote my 12 as 2 times 6. I wrote my 18 as 3 times 6. I see they have a 6 in common, so I cancel them out. Okay? Let's do the exact same thing for this example with the letters in it instead. Well, you already factored the bottom, right? We already did that a minute ago, didn't we? The x squared plus x plus minus 6, we already factored that when we solved the equation. Let's do the exact same thing on top. What does the top factor as? Good, x plus 5 and x minus 2. Right, again, we've got a quadratic with a leading coefficient of 1, so I know I have to have x and x as my first pieces. I need things to multiply to -10 and give me +3. So I need to use plus 5 and minus 2. Do we see now common factor on top and bottom? The x minus 2. Just like we saw the 6's here, right? Okay. The x minus 2's are in common, so we can divide those out and get x plus 5 over x plus 3. as our final answer. So just like when you did fractions before with numbers, you factored and canceled to put it in lowest terms. You would literally do the exact same thing, factor and cancel. Okay. Now be careful. When I say cancel, I really mean divide out common factors. A lot of students will want to say, oh, my x squared's cancel here, because I have an x squared on top and bottom. That's not canceling. You cannot divide out individual terms on top and bottom. Okay? You have to have products that divide out. Okay? So be careful with that. Don't say, oh, I can cancel those and I can cancel those. That doesn't work. Okay? That's not a product. Okay? If I need an example with numbers to show you what I mean, some students like to do something like this. Make a 1 and a 1 and get 1 plus 4 is 5. That's bad, right? Okay? That's because I'm trying to cancel out individual terms, right? That's not a multiplication there. So you can't, if I can't do it with numbers, I can't do it with letters. Okay? Things have to be multiplied together to divide out. Okay? So be careful with that. This is trash. Okay? All right. So let's see if we can do these next couple together, and then I'll turn you loose on a worksheet. Pardon me. Notice in number 1, things are already factored for you, right? So do you see any common factors on top and bottom? X minus 7. They go away. Reduce the lowest terms. We get x plus 4 over x plus 2. Those divide each other out. That one was pretty straightforward, wasn't it? Let's see if we can do another one that's, well, let's do the next one just in line, because it's a little bit different. Let's do this one. Again, when it asks you to convert or reduce to lowest terms, literally it's just asking you to factor everything in sight. Okay? Factor the top, factor the bottom, see what divides out. Okay? And we're going to see that again on Monday, too, when we do multiplication and division. It's going to be the same premise. Factor everything in sight, see what cancels out. Okay. So let's factor the top and factor the bottom. How does the top factor in this case? X plus 1 and x plus 5. Again, remember when it's a leading coefficient of 1, I know it has to start with x and x. How does the bottom factor? Good, x plus 1 and x plus 7. And then again I ask, do you see anything in common? X plus 1. So those are going to go away, and we're left with x plus 5 over x plus 7. That one okay? Okay. Let's do number 3 here. Again, when you're doing factoring, the first thing you should look for is a GCF. Do you see a GCF on top? 4 leaves you with x minus 3. And what do you see for a GCF on bottom? And leaves you with 3 minus x. Everybody see that? Okay. Right now, I don't think I see a common factor, but it's close, right? Okay. You see what I mean? X minus 3 and 3 minus x aren't exactly the same thing, are they? No. But how do they differ? Well, I've got a positive x on top and a minus x on bottom. I've got a minus 3 on top and a plus 3 on bottom. So really, this is the negative of that, isn't it? Okay. So if we would have instead factored out a negative 5 instead of a 5 on the bottom, say, if we pull out a negative sign, that changes the x to positive and the 3 to negative, doesn't it? You see it? And now your x minus 3's go away. The main reason for this example being included is just to be careful with that one. These are not exactly the same, but they are opposites of each other. Okay. Now, along those lines, this is one of those that could get a little bit tricky, which is why I'm mentioning it. If you had something like x minus 3 and x plus 3, is there anything that we can do to try to cancel those out at all? Are those exactly the opposite of each other? Are the x's exactly the opposite? No, they're the same, but these are the opposite, right? You can't do anything with these. This is as far as you can go. There's nothing in common with those. So as I said, it gets a little bit tricky, doesn't it? Right? What I mean by exactly the opposite is that every single sign has to be different. Right? That would be exactly the opposite. Minus 3 plus 3 plus x minus x. Those are exactly opposite of each other, right? These are, the 3's are opposite, but the x's aren't. So there's nothing I can do. That's as good as it gets. Okay? So that's why I said it gets a little bit tricky, so you have to be careful with those. See if you can do number 4. Same premise, factor the top, factor the bottom, and see what you get. Then we'll chat about it. And while you're working on that, I'll hand out the worksheet. Sorry, Kevin. You ready to chat about this one? Yeah. All right. So, well, how does the top factor and how does the bottom factor in this case? What is your top factor as? When you got your factorization. Okay, 2x minus 5. Or should be x minus 5. There we go. And 2x plus 1 is whatever we got for that factorization. We need to do it off to the side over here, right? That's what I was starting to do over here was the AC method. 2 times negative 5 gives you negative 10. So we need things that multiply to negative 10 that give you negative 9. What works? What multiplies together give you negative 10 and adds to negative 9? Yeah, negative 10x and a plus 1x. Good. So you'd have minus 10x plus x minus 5, right? Then we can factor out a 2x, x minus 5, and we have 1 times x minus 5. So we get that. So I said that factoring is important, right? It's going to be the crux of everything we're going to do here. How did the denominator factor? Good. Again, here if I do AC, 2 times 7 is 14. So any things that multiply to 14 and add to 15, what would you use? 1 and 14. And then again, we would do our factor by grouping and get our factorization. Do we see anything in common? The 2x plus 1, yep. And so then we divide those out and get x minus 7, or excuse me, x minus 5 over x plus 7. Again, if you need to, absolutely please write the factorizations out off to the side first, right? Get your numerator factored, get your denominator factored, and rewrite your fraction. If you do it that way, please do it that way. The whole point is to get to the factorizations, right? Any questions on that one at all? Well, go nuts on your worksheet there that I gave. I'll get some answers posted here as we go so that you can check your work as we go. Holler at me when you've got questions. Happy to answer. I'm always happy to answer.